Welcome to lecture number 9. Today we want to talk about the superposition of clocks in the gravitational field. So let us start coming back to what we already discussed excessively in the previous lectures. Let us think about the cow experiment again. But in a slightly modified version. Let's think we do an experiment in the gravitational field of the Earth. We have a particle, we split it up in the gravitational field. In some way, and we bring it back together. So you know from the cow experiment, basically the particle that's lifted up to a higher potential will acquire a phase difference compared to the lower potential. So this one needs energy in the gravitational field, and then its phase progresses slower than it does in this case, where it gains energy from the gravitational field. So the phase here will be ahead of the phase here. But you can, in the cow experiment, you can just compensate for this phase difference by making this path a bit longer, just in a way that at the end here you get a delta phi of 0. So we do our cow experiment, but we choose the path length such that in the end we get an interference pattern. But now think of doing this experiment instead of doing it with a single particle, as we did in the cow experiment. Think of doing this experiment with a clock. A clock can be any system that has some internal degree of freedom, that has some periodicity, from which I could somehow read the time. So think of a physical clock, but you could also have, say, an atom that has some decay process or some oscillatory process. That allows you to somehow draw a conclusion on how much time the particle spent along this trajectory. So if you have such a clock, degree of freedom here, then you know from general relativity that now those two different paths in the gravitational field will have different proper times. So the proper time that an observer sees along this trajectory 1 is some tau 1, and an observer that follows the second trajectory will see a different proper time, will measure a different proper time, tau 2. Now, you also know that if you have solutions, stationary solutions of the Schrödinger equation, for example, their time dependence is just given by a phase that is e to the I times energy times time divided by h bar. So they have an oscillatory phase that just oscillates in time with the total energy of the system. And of course, in a non-relativistic situation, so you have this oscillation factor, but it's just a constant, like it's at any given time, it's just a constant, so it just oscillates the same along both trajectories. So this term really doesn't matter for our interference pattern. It will just be exactly the same phase difference here, no matter where we look at our wave function. If we look at it at the same time, then this will just be the same phase for both paths. But now in general relativity, we have this difference in proper times. So the idea is basically if we have something that oscillates here, or if we have a phase that would oscillate, then this difference in proper time will show here in a phase difference of our wave functions. So we will get an additional phase difference in addition to the cow phase. So this is basically the idea, or more intuitively speaking, you could also say, we know as a principle of quantum mechanics, we get an interference pattern if we cannot tell which path a particle took. So if we don't have which path information. If we gain with which path information, for example in the double slit experiment, if we have some device behind one of the slits that can tell us, that indicates, yeah, the particle took this path, then we destroy the interference pattern. And the same one would expect to happen here if I have a clock, and if by looking at the clock afterwards I can tell if my clock took the upper path or the lower path, because it will show a different time depending on which path it takes. Then I get which path information from this clock degree of freedom, and I should lose the interference pattern. So this is the idea, and this is what we want to look into today. And in fact, if you do this and you would just take the rest mass energy here, actually let me be a bit more explicit. So let's look at the following. In general relativity, we would describe those two trajectories, or in general, we have some metric that describes our space-time, and with this metric, we have a line element. And if we go along one of such a path, we can give this line element in terms of the proper time, so it's minus c squared d tau squared, which and the definition of this line element is that it's minus g mu dx mu dx mu. So it follows from the metric that we have, and from this we can get an expression. We can take the derivative d tau by dt, so we can see how the proper time along our trajectory depends on the coordinate time, or varies with the coordinate time. And this expression gives us 1 divided by c. So dt is just the x0 variable here, right? So taking this derivative, we get 1 over c square root of minus g mu nu dx dot mu dx dot mu. So those are the derivatives of the components x mu, of those objects by time. And now the important part is that if we have a Newtonian gravitational field, so we would assume again that we have linearized gravity, so we can write our metric as eta mu plus h mu, and we find again that we have an h00 that's proportional to our gravitational potential phi. So we have a Newtonian gravitational potential. Then we can calculate d tau by dt, and we get that this is 1. So in the non-relativistic case, t and tau are actually the same, minus v divided by 2c squared. This is what we call special relativistic time dilation. This is the time dilation because of a finite velocity that's close to the speed of light that we have in special relativity. And now comes the term that is gravitational time dilation, which is phi divided by c squared. So we have these corrections to the proper time along our trajectory. So because of those, we have a difference in proper time along the two. And now if you see, if you have a factor here, you have a delta, you have a phase difference that is basically proportional to the energy times the difference in proper time. And now if we remember that the energy is in a non-relativistic situation is at lowest order is mc squared. It's just the rest mass energy. So if we use this together with this, we just get m as phi. So we just get our cow phase that is proportional to mgz in from this relativistic expression for the energy. So basically we can understand the phase in the cow experiment also. So this is different than the derivation we had, right? We did basically a non-relativistic derivation where we considered plane waves in a Newtonian potential. And then we did a fully relativistic derivation where we looked at the phase of a Klein-Gordon field in general relativity. And now we have a third explanation of this cow phase, namely that it is an effect of time dilation, of a difference in proper times. And it's like the non-relativistic, the leading order contribution. It comes from the rest mass energy together with the difference in proper time because of the gravitational potential. So this is another way to understand the cow phase. And this is interesting now mainly because once we've established that, we can think about relativistic corrections. And now we can think of what happens if, well, we look at the actual, the zeroth order term that comes here in the energy will also couple to this. Yeah, and to this, and this will give us 1 over c squared corrections. And and this is what we want to talk about in this lecture. So this was the executive summary of what we are doing. So let us look into this in a bit more detail. So our goal is now to find a reasonable description in a Hamiltonian Schrödinger equation formulation of this problem of a clock, of a particle that has an internal degree of freedom. As a first step, we want to look at the relativistic point particle and its Hamiltonian. And before we do that, we look at we just discuss very briefly the non-relativistic case. So in the non-relativistic case, remember, we can introduce the Lagrange function L, which is kinetic energy minus potential energy. So for a point particle which has a coordinate x and some potential, this would be 1/2 mx dot squared minus the potential v of x. And now we can define canonical momentum with components pi, I going from 1 to 3 again. So the pi component of the momentum is just the derivative of our Lagrange function by the velocity in I direction, so dl by dx I dot. And of course you see immediately that this is just m times xi dot. So this is just standard mechanical expression for momentum. And now we can get the Hamiltonian for this point particle. The Hamiltonian is obtained from the Lagrange function by a Legendre transformation. So this is pi xi dot, where I use the summation convention again. So we have to sum over I from 1 to 3 here. Yes, pi xi dot minus L. And this again we can calculate, and we get the well-known expression. So we get p squared divided by 2m plus v of x. Okay, so this is all, of course, very unsurprising, but just as a recap, how starting from the Lagrange function, you get the Hamiltonian, and once we have this Hamiltonian, this is actually the Hamiltonian that enters in quantum mechanics, that describes enters in the Schrödinger equation after what is called canonical quantization. So the rule for canonical quantization is that we replace the occurrences of our quantities, of our classical observables x and p, by the corresponding operators. So for example, in position space, our vector x becomes the x operator, and our vector p becomes the operator minus I times gradient. And and we can insert this, and we get the Schrödinger equation in the usual form. So we get IH bar time derivative of the wave function equals this Hamilton operator. So this would be minus h bar squared Laplace operator divided by 2m times psi plus v psi. Okay, so this is how we end up with the Schrödinger equation, just in like a very thorough explanation. And now we can try to do the same for the relativistic case. So in the relativistic case, we can write the Lagrangian as minus mc. Minus mc times the square root of minus eta mu nu x dot mu x dot nu. So this is the relativistic point particle Lagrangian. Again, we can calculate the canonical momentum from this. So we get, if we again take the derivative of L by the components xi, and you can write this as mc xi dot divided by square root of c squared minus x dot squared. So this is the expression for the momentum. What we want is we want to invert this. We want to find x dot as a function of p in order to get the Hamiltonian. To do this, you first calculate p squared. So p squared is m squared c squared x dot squared divided by c squared minus x dot squared. And now from this we can get x dot squared, and then we insert this here and solve for xi, and we find xi to be PIC divided by m squared c squared plus p squared. Okay. So now we have the positional momentum, and again we can now get the Hamiltonian. Same way as before. So pi xi dot minus L. So we have to sum I from 1 to 3, and if we calculate that, you find some more in between steps in the lecture notes. I just give you the result. Again, unsurprisingly, you find the relativistic energy expression. So you find square root of n squared c to the 4th plus p squared c squared. So this is all fun and rather unsurprising, because we're just doing classical mechanics here. So the expected outcome is that we find the Hamiltonian for the relativistic energy expression. So the problem we run into now is, if we now try in the next step, if we now want to canonically quantize, so we want to replace our p by an operator, we are left with this square root of the Laplace operator. And I mean, there are mathematical theories that try to deal with such expression, but it's not something that is physically very useful. So this is the reason then why normally in relativistic quantum mechanics one moves on to the Dirac equation or the Klein-Gordon equation as the relativistic equation to look at. But what we can do with this Hamiltonian is that we can expand it in powers of 1 over c squared. And if we do that, then we get at the lowest order just mc squared, so the rest mass energy. Plus the kinetic energy, the non-relativistic kinetic energy, p squared divided by 2m. And then the first relativistic correction term is minus p to the 4th divided by 8 m cubed c squared. Plus higher order terms in 1 over c squared. And this then would be perfectly fine, again, to just substitute p squared by the Laplace operator. So from this we would expect that we get a Schrödinger equation, and we'll squeeze this in here. So we get the standard non-relativistic Schrödinger equation, and then we get a relativistic correction. That would be minus h bar to the fourth divided by 8m cubed c squared. And then we get a double Laplace operator from this p4. Okay. So this would be the relativistic correction to the Schrödinger equation according to this approximation. So we could work with this and calculate relativistic corrections. So this is our first observation. So contrary to the non-relativistic part, I did not include any potential here. Right? You can't do that as easily. You cannot describe interactions easily with a potential like you can in non-relativistic situations. We were just concerned about the free particle here. And we can leave the rest mass energy term out. If you would include this in the Schrödinger equation, this just gives you a constant here, which just gives an unobservable constant phase. It just gives an overall phase to the wave function that is not observable. That's why this mc squared term does not appear in the non-relativistic Schrödinger equation. Okay, so we have the Schrödinger equation to first order with corrections in 1 over c squared. And now let us discuss what the implications are if we want to look at the Hamiltonian for a clock in a gravitational field. So the first thing we do is that to the Hamiltonian that we just found, the 1 over c squared order relativistic correction to the Hamiltonian, which I call H0, to this Hamiltonian we add the gravitational potential. So we have in Hamiltonian H0. We also include the rest energy, mc squared, for reasons that will become obvious in a minute. So we have mc squared plus p squared divided by 2m minus p fourth divided by 8m c cubed. So 8m squared c cubed. And now we add the gravitational potential, so we have plus m phi. With just the Newtonian gravitational potential. So you already see that there might be some inconsistency here. We have a relativistic correction to the free Hamiltonian now, but now we just include a Newtonian gravitational potential without any relativistic corrections. So we will need to discuss in the end what this actually means and if there are any problems with this. But for now, this is what we're working with. And now the question is, how can we use this Hamiltonian if we want to describe a clock? So we want to describe some system that is not just a point mass, not just a point particle, but it has some internal degree of freedom. And what we expect is, so the internal degree of freedom means it has some internal energy. And this internal energy should somehow couple to our system. And you know in relativity that the mass that appears in the equations as the both as the inertial mass and as the gravitational mass, the mass isn't or not just mass is gravitating, but also energy is gravitating, or also energy contributes to inertial mass. So what we can do is we can replace our rest mass energy for a point particle. We can replace this by the rest mass energy plus the internal energy of our clock. And I call this small h. So small h is the Hamiltonian for our internal system, the Hamiltonian for our clock, or the internal energy of our system. So instead of having the mass, we have the mass plus the internal energy divided by c squared. So if we make this replacement in this equation, again in the lecture notes you have the full calculation, but after this replacement, you can effectively write the Hamiltonian. So you effectively find the Hamiltonian h. It is h0, which we had for the point particle, plus some term that is first order in this correction h. Again, plus higher order terms. Plus higher order terms in the speed of light. And then this gamma here that couples to the internal Hamiltonian is the following. It's 1 minus minus p squared divided by, I need to copy this, divided by 2m squared c squared plus phi divided by c squared. And so this, we get this out by just replacing the mass here with mass plus the rest energy. So you see, if we do this in the rest mass energy term, then we have an order c squared. We have an order c squared effect here. So this gives us mc squared plus h. So this is where the internal energy comes in our total Hamiltonian. So this is the 1 here in our gamma. That's kind of the non-relativistic. Yeah. So this is the non-relativistic contribution of the internal degree of freedom. It's just it doesn't couple anything to our h. It's just the internal energy added to the Hamiltonian. But then we get relativistic corrections. To that. We get terms that actually couple. So those come from replacing the mass here and here and here. So we get a coupling of the internal energy to momentum, and we get a coupling of the internal energy to the gravitational potential. And those are those two expressions, and you can actually understand them again as the effect, if you want, as the effect of a special relativistic time dilation, or a special relativistic effect and a general relativistic effect. So they are in some sense related to time dilation, but it's not very obvious. So they are sometimes linked to that in certain papers that discuss this topic. I don't like this association so much actually, because it's not, to me it's not obvious that you should call them time dilation, other than that the gravitational effect is again the same as what we saw before when we looked at this at the metric element and the difference in proper time. So you could explain it that way, and it gives you the same numerical result, but it is not obvious from this derivation in terms of the Hamiltonian why you should call this time dilation. Anyhow, so what we have is here is a relativistic correction to our Hamiltonian that gives us a coupling. First, a coupling of, so this is basically the kinetic energy, the center of mass kinetic energy of our particle. So the kinetic energy of the center of mass of our particle couples to the internal energy, small h. And the same way, if you think the potential here in general will be a function of position. most, like in the easiest case, if you just have the homogeneous potential m times g times z here, then this is just linear in position. But so in any case, this will give you a coupling of the center of mass position of the particle to the internal Hamiltonian. So we have these two types of couplings. We have from the special relativistic effect, we get a coupling between center of mass energy and internal energy. And from gravity, we get a coupling of center of mass position and internal energy. And now we can look at an example to understand what the effect is of such a coupling. So to look at a concrete example, and I just write as a reminder here, I copied that we have h equals h0 plus the term where our internal Hamiltonian interacts with a center of mass, term gamma. And now as a concrete model, we think of our clock or our internal degree of freedom being a two-level system. So our h we can write as some energy value E1 with the projector on some state which we just call 1, and the same for state 2. So we have we have the energy basis for our operator is just the energy that goes with the first state times the projector on the first state plus the energy that goes with the second state times the projector on the second state. And we assume that we have an initial state of our clock which we call psi clock, which can be any superposition of those two energy eigenstates. So an arbitrary state that is characterized by two constants alpha and beta, and we express it in this energy basis. Now our total state, we call this psi 0. Our total state is supposed to be at the beginning, is supposed to be a product state. And we look at the situation, we think of the cow experiment-like situation where our particle or our system or clock can follow two different possible world lines. So the state of the center of mass we can describe as a superposition 1 over square root 2 gamma 1 plus gamma 2, where those two represent the two possible trajectories that our particle can take. And then we have a tensor product with this clock state. And now we can look at the time evolution of the state. So if we look at the state psi after some time t, then we can just from the Hamiltonian we find immediately that this psi t is the exponential of it divided by h bar. And now in principle we have the Hamiltonian acting on psi 0. So this would be in general the time evolution operator. But now we assume that our trajectories here are effectively stationary states, or are basically or rather, let's say that the time evolution of a particle along the trajectories is already encoded in these states. So basically H0, or free Hamiltonian acting on gamma 1 and gamma 2 doesn't really do anything. So it just gives us the same state back, because these trajectories describe are basically given by the Hamiltonian H0. So then what we are left here is just this correction term gamma H. And now we can take the non-relativistic case, where gamma is simply 1, and the whole Hamiltonian separates in the center of mass and internal degree of freedom. And in this case, you see that that this operator here acts only on the clock degree of freedom and not on this one. So our psi t will just be the same position state. Tensor a clock state that evolved, and now if you apply this operator with gamma equals 1 to this state, what you get is alpha times, and this state 1 evolves with the energy E1, so you get e to the I E1t divided by h bar. It's 1 plus beta e to the I E2t divided by h bar times 2. But now, if we look at the relativistic situation where we have gamma, then this gamma also acts on the center of mass part of the wave function. So in this case, we need to write our psi t as 1 over square root 2. And now, after acting on the clock degree of freedom, we get alpha times e to the it divided by h bar E1 from the small h operator times gamma. This is a bit hard to read still. I hope the board will dry in a minute. I continue writing already and then I explain. So we have we get E1 here and E2 because our states 1 and 2 are eigenstates of our small h operator, but we have this gamma here still. So this is still an operator that acts on the center of mass states gamma 1 and gamma 2. So our state does not separate anymore, as it did in the non-relativistic case, into a clock state with some oscillation and the unperturbed or unaffected state of the center of mass. But now we have a clock energy dependent operator here that is still acting on our center of mass state. And if we want to understand now just the motion of the clock, so just how the clock moves in position space, or just what the center of mass of our clock does, then we need to calculate the reduced density matrix. So we need to trace out the degrees of freedom of the clock. So let us do this. So we need to calculate the trace of the pure state density matrix that belongs to psi t. We have to trace over those two states. 1 and 2 are the two possible clock states. So we get this term, the projection of 1 on psi 2 times the complex conjugate, plus the same with the state 2. Now we can calculate this. So for the first term, only this part of alpha survives. So here we get an alpha. Here we get an alpha complex conjugate. We get 1 divided by square root squared, so we get 1/2 for all those terms. And then and then we get an e to the I1 gamma from the left, and if we take and here we get an e to the -1 gamma acting from the other side on our gamma 1 gamma 2 state. Sorry, the other way around. So this one gives us the complex conjugate e to the -I, and this one gives us e to the plus I E1 gamma, acting from the left and from the right. So in total we have alpha squared half then this operator once. And now here we get the product. So we get actually all 4 terms. We get gamma 1 gamma 1, then we get gamma 1 gamma 2. And so on. So those 4 terms. And finally we have e to the minus it divided by h bar E1 gamma, acting from the left here on this state. And then I just put dots here. We have plus the same with beta and 2 everywhere. So and now we can expand this. So what we do now is we expand this in gamma to linear order. Because we know that all higher order terms in gamma, so if, gamma itself is already of order 1 over c squared. So higher order terms in gamma, in terms of gamma squared and so on, are not part of our first order first order relativistic approximation anyways. So just linearizing this. What we get in the lowest order, and I skip one step now that you can find in the lecture notes. So at the lowest order, you just get the following density matrix. You get 1/2 times times this, so you get a 2 by 2 matrix that has 1/2 in each entry. And now there is a correction term which you can write as IT divided by 2H bar. Then we have alpha squared E1 plus beta squared E2 and then we have a commutator from expanding this exponential. Remember, you have to use the correct expression how you write an exponential of an operator. So you have to use the Baker-Hausdorff formula, and you get these commutators. So you get the commutator of gamma with and what actually survives here are the two off-diagonal terms gamma 1 gamma 2 plus gamma 2 gamma 1. So this is our result for the density matrix. So we only have gamma 1 gamma 2 and gamma 2 gamma 1 here because the other two add to unity. So this one plus this one just give us a 1, and then those two terms cancel, and then you have alpha squared plus beta squared equals 1. So those terms will just add to a constant contribution, and now we have, sorry, the commutator will disappear, they will not add to a constant, so the commutator of a constant is 0, of course, so the operator 1 commutes with the operator gamma. So now we have the density matrix here in this case, and again you see that in the non-relativistic case gamma is simply 1 and this commutator vanishes, gives us 0. So we just have this density matrix that also describes the situation if we wouldn't have the clock at all. So in the non-relativistic case there is no effect of the clock. The clock can do whatever it wants. It can show whatever time it wants, and it's also in non-relativistic situation, it just ticks with the coordinate time t, right? So whichever trajectory our particle takes, the clock will do the same thing regardless of the trajectory of the particle, and in the end it will not have any effect on our interference pattern. And this is basically also the expression of that our total state separates in those two, in clock and center of mass degree of freedom. But now if we take this relativistic effects into account, then we see that we get this entanglement, we get this term gamma times small h that entangles the center of mass degree of freedom with the clock's energy. And this leads to this additional term in the density matrix, and you see here this has a similar shape than the equation for the density matrix that you saw at the beginning for collapse models. So this is also an equation. You see it affects the off-diagonal terms of the density matrix. So what this actually does is if there is an energy difference between those two states, if there is a difference between E1 and E2, then this will suppress the off-diagonal elements. So it will lead to a dephasing or to something that looks like a decoherence effect. So an interference pattern will disappear because the off-diagonal terms in the density matrix disappear. So the effect that we've seen generates from a genuinely relativistic effect. So it really comes from the relativistic corrections to the Hamiltonian. And if you look at the gravitational part of it, so the coupling to the gravitational potential, you can say that this is generally a general relativistic effect. Despite the fact that we just have the Newtonian gravitational potential there, we would just add phi to be the Newtonian potential. But it is an effect that comes from relativistic corrections of our Hamiltonian. So it's essentially a time dilation effect. So in that sense, you can say it's a time dilation effect in the Newtonian potential. And despite the fact that there is no space-time curvature here, it still would be something that goes beyond what has been tested in the Cow effect. Because of that, it's also important to make sure that what we have been doing has a proper foundation. And you have maybe noticed already in the derivation that there are some things that you should maybe put a question mark behind in the derivation. And one particular thing is that we just made this ad hoc replacement of replacing the mass by mass plus internal energy, right? So this is of course intuitively clear if you take a relativity seriously, but we would like to have or to see in a more rigorous way how these effects follow from general relativity and quantum systems. And in principle, so there is we are still not talking about the gravitational field of quantum matter. We are still only talking about how does quantum matter move in a gravitational field. So we have an external space-time background given, and we are asking what is the behavior of quantum matter. And we could do quantum field theory on curved space-time. That is a theory that is being studied, and that would certainly satisfy our need for having like a fundamental theory from which we can derive things. Unfortunately, that theory is still not that well understood, and it's very difficult to derive anything from it that has applications in a non-relativistic or in a laboratory situation. So if you ask the question, okay, what would I observe in a lab? Then it's not really a feasible way to start from such a quantum field theory and curved space-time model. So the question is, what can we do to get a more rigorous derivation? And there are two main questions that we want to address. So the first question is, how do we model the relativistic dynamics of a quantum many-particle system? Because we had an internal degree of freedom here, so we are basically talking about complex systems that constituted of many particles. So how do we model the relativistic dynamics of such systems in a curved space-time? But then we were looking at the effect on the center of mass degrees of freedom. So the second question we have to ask is, how do we find from this the dynamics of the center of mass? And those will be the two issues we will address in the next lecture. But to motivate them already, let me first give you a brief recap of how we do this normally in general relativity. And this is called the minimal coupling scheme. And it's the normal way how in general relativity, if you have matter and you're interested in how does this matter, how do you properly couple this matter to the dynamics of space-time, then you do this in essentially 4 steps. The first step is you find a Poincare invariant formulation of the dynamics of your system, of your particle, field, whatever you have. So you need to write it in a way that is compatible with special relativity, that is special relativistically invariant. So. So we need a Poincaré invariant form of the dynamics of our system. A typical example would be to have a relativistically invariant Lagrange density, for example, for our system. And then, if you have this, then the second step is you just replace the metric, the Minkowski metric in flat space, in special relativity. You replace this by your curved spacetime metric, G mu, and you replace the partial derivatives that appear in your Lagrangian, your equations of motion, whatever. You replace all the partial derivatives by covariant derivatives. That, if you remember, again, are partial derivatives plus some functions of the metric. So if you have a given metric, then you can do this without problems. And then as a third step, you derive the stress energy tensor that goes with your metric. So the stress energy tensor is proportional to the derivative of the Lagrange density by the metric. What's in front of it depends a bit on which convention you choose, but yeah, you can derive a stress energy tensor, and then you have all the ingredients to, in the fourth step, solve Einstein's equations. So then you get the back reaction of matter on space-time. So you see how your space-time metric reacts to the matter field. And you solve the equations of motion in this curved space-time. So we don't even really need to do those steps. We already these steps 3 and 4. We are already happy with just having an external spacetime and ignoring the back reaction and just talking about the dynamics of our particle. So we would be fine just going to here. But in fact, the problem with quantum mechanics already is in step 1, and it is that there is no such thing as a Poincaré invariant or a special relativistic version of a fixed number of particle quantum mechanics that has interactions. So as soon as you have interactions between particles and you want to have relativistic corrections, you always get particle creation and annihilation, and that's why essentially you need quantum field theory to describe these types of processes. What you can do, however, and this is what we want to talk about next time, is you can look at situations where the particle number is approximately conserved, so where you can neglect all these particle creations and annihilation processes. And you just are dealing with a fixed particle number the whole time. And then you can ask, well, in those situations, can I somehow, in an approximate way, still get some description of my system that is in some way relativistic. And this is what we will deal with next week, where we're showing that we can, where we use the fact that we know that if we have a relativistic equation like the Klein-Gordon equation, we can get the Schrödinger equation out as the non-relativistic limit of this. So we start from the assumption that if we would start with the Klein-Gordon equation in curved spacetime, which we can formulate because it's a Poincare invariant, and then we take the non-relativistic limit from this curved space Klein-Gordon equation, that then we end up with some different version of the Schrödinger equation that also contains these curved spacetime effects. So this is what we want to do in the next lecture, and I'm happy to see you then.